In this video, we're going to find the distance between the plane given by the single linear equation 2x minus 5y plus c is equal to 3, and the point in space, which I've called S, whose coordinates are 1, 1, and 1. In order to get started in any of these kind of problems, you want to just draw a generic picture to help you conceptualize the information you have available and the information you want to derive. In this case, I have a plane and I have a point. Not much to my picture there at all. I'm not trying to draw it accurately. I took a big guess here that S is actually not on the plane itself. That's the most likely situation, but if it was on the plane, we'd probably figure that out later on when we do some calculations. Don't try to be accurate here with your pictures. The distance that we're after is what I'm calling d here. You get by drawing a line segment from S to the plane meeting at a right angle. So we want to make sure that we are definitely meeting at a 90-degree angle when we do this. I don't want to take some other trajectory to the plane from my point, as that would be a longer distance. So d, the distance that we're after, is this projected distance at a 90-degree angle. Now I have the equation for my plane. Its coefficients are 2, minus 5, and 1. And reading the coefficients from an equation for a plane immediately tells you a normal vector to the plane. I'm going to call that vector n, and its components are 2, minus 5, and 1. Again, I'm just reading them from the coefficients of my equation. Now, the distance that I want is, in my picture, drawn over here, but it's just a distance. So I'm actually going to kind of think about it as being an extension of where I've drawn this normal vector. So there's this distance here that I want to get at, and I'm drawing that as a vector, kind of like it looks in my picture like a longer version of my normal vector. And if I find a point on the plane, any point, I'll call it P. It really doesn't matter. We'll find one later. And find that vector P to my point S that I want to measure the distance from. What I want to do now is I have a right triangle, and I really am trying to find this side of that right triangle that's showing up here in this picture. What I really want to do is kind of project that vector PS, the hypotenuse of that right triangle, onto the direction determined by my normal vector. So the distance that we're after is the length of the projection of this vector PS onto my normal vector here. And because all of this is sitting in some sort of right triangle, and if I focus on the angle between these two vectors, I should be able to relate it to the appropriate trig ratio and therefore the appropriate vector operation. Yeah, I'm going to call the angle between the two vectors theta. I have a right triangle, and the side that I'm interested in is this side here, that is the adjacent side of that triangle. So the length that I'm after is the length of the vector PS, the hypotenuse of the triangle, times the cosine. The adjacent side, remember, was what we were after, so the cosine of theta. This reminds me of the dot product of two vectors because I see the cosine. So I'm going to put a factor of the other vector in here that's forming that angle, and I'm calling it, so the length of n appears in there. So I'm looking at the vector, the angle between these two vectors, and I've just introduced the length of that one in there. But to make this equal now, these are no longer equal. I've messed up my equation here. I need to divide by the length of n. And I've done that precisely because now it's the dot product of my two vectors in the numerator. Remember that the dot product of two vectors is their lengths multiplied together times the cosine of the angle that they form. So in the numerator I have ps dot n, and then I've got to divide by the length of n. It should make sense that we're dividing by the length of n here because the normal vector is only determining the orientation of the plane. It's only determining the direction that I'm projecting down onto. And so somehow we have to normalize our expression by dividing by the length of that vector. Now there's a slight technical issue here. It could be that my vector PS and my vector n are actually on opposite sides of the plane. Maybe my normal vector is actually pointing on the other side. That angle theta would be huge. It would be obtuse. And the cosine would in fact be negative. The dot product would be negative. But you'd still be getting the length itself. You'd just be getting the opposite of the length. So when I say distance here, I'm going to add the word signed length here, just to indicate that if I was to get a negative value, I would interpret it as the opposite of the length that I'm looking for. And that occurs when the angle is in fact obtuse. Let's do our calculations now. We know our normal vector. It's 2, minus 5, and 3. We need a point on the plane. That's the missing ingredient in our picture, this point P. There are infinitely many. Pick one. I am going to see, I'm just going to take a leap of faith here, is there a point whose x-coordinate and y-coordinate is 0, and in fact if I take x to be 0 and y to be 0 in my equation for my plane, my z-coordinate must be equal to 3, and so that tells me that the point 0, 0, 3 is in fact on the plane that we're looking at. Now I'm going to find my vector PS. I look at the displacement as I go from P to S, so I'm going to take 1 minus 0. I'm going to take 1 minus 0 again, and I'm going to take 1 minus 3 for the third component, and I get the vector 1, 1, minus 2. I need their dot product, so I'm going to take the corresponding components of PS and N, multiply them together, and add the result. So 2 times 1, minus 5 times 1, minus 2 times 3, so I get minus 6, and all day that will give me a scalar quantity called the dot product of the two vectors, and that is minus 9 here. Notice I get a negative value. The fact that the dot product is negative is telling me my picture is somewhat inaccurate, that the cosine between, or sorry, the angle between these two vectors is actually bigger than 90 degrees. It's obtuse. And so these vectors are actually on the opposite sides of the plane. The final quantity that we need is the length of the normal vector. We need to divide out by that, and I sum up the squares. I'll take 2 squared plus 5 squared plus 3 squared. Take the square root of that, and you get the square root of 38. And so the distance that we want is minus 9 over the square root of 38. Well, that's not quite right. I need to take the absolute value of that because I have this issue with the angle being so large, and so the length is really positive 9 over the square root of 38.